Hi, my name's Carlton Coffrin. In this video, I'm going to tell you a little bit about some exploratory work my colleagues and I have been doing on using convex relaxations of the AC minimal load shedding problem for severe contingency analysis in AC power networks. This talk is intended for a general power systems audience. Before I get into the problem that we're interested in, it's important to understand a little bit of the context of what we're doing and where we work. So all of the people involved in this project work at Los Alamos National Laboratory, which is funded by the Department of Energy and the Department of Homeland Security, among others. So these agencies tend to ask very different questions about critical infrastructure and power systems than a typical utility would. So what's our motivation for this work? The primary motivation is the threat of natural disasters on the United States infrastructure. You can see that these natural disasters are really large and they can have very severe impacts to a wide range of people across the United States. One of the most common questions that people are asking is how bad is it going to be? So for example, you can have a hurricane forecast a few days out, which you can see on the right here, and then you have kind of a typical operating condition on the left for Puerto Rico. And then after this particular hurricane hit, this is what the power usage looks like across Puerto Rico. So one of the big questions that people want to know is how severe is it going to be, and do we need to bring to bear, say, the Army or FEMA to help out in this situation, or can the local utilities take care of it on their own? Another major challenge of modeling these natural disasters is that they're very large scale, so they cover a huge geographic area. On the left, you can see all the different regions that Irma influenced when it hit the United States in 2011. Another big challenge is that these events can be incredibly costly, so better understanding can go a long way to improving quality of life post-disasters. Another interesting use case these kind of government agencies are interested in is targeted attacks. One of the most famous cases was this Metcalf sniper attack in California, where a sniper shot the tanks of transformers in a substation nearby San Jose. And in the worst case, this kind of damage could cause an overload, which set a fire or damage the whole substation. This is only an illustration made by CNN of how bad it could be. In this case, things did not actually catch on fire. So the main questions that these agencies want to know are twofold. First, they want to understand the vulnerabilities. So in the event of these types of natural disasters or targeted attacks, how bad could things be? And then after that, they want to answer, how can we mitigate the potential damage of those disasters? So building these thicker walls is one example of how the sniper attacks have been mitigated. Now in this talk, we're going to focus specifically on just understanding vulnerability. So we're not going to go to the mitigation step yet, but that's something that would be interesting in the future. So let's talk a little bit about the challenges of doing a vulnerability analysis on an AC power network. First, here are some things we know. We'll have predictions of what's going to happen. So in the case of a hurricane, this would be something like a NOAA storm track, where they've run a number of models and they've predicted exactly where they expect the hurricane to go and how it will evolve over time. We also have these FERC 715 filings. These are extremely detailed network models of the US infrastructure at the transmission level. So this is a very high aggregate level of power. So the simplest thing I can think of for doing a vulnerability analysis on with this type of information is first we simulate those hurricanes based on this NOAA forecast. Then we estimate the damage we would have to the transmission system as a consequence of those particular simulations. And then we use the power network information we have from FERC to run power flow simulations. You could use potentially any one of these commercial or popular open source tools to do that sort of analysis. So let's just zoom in and look exactly how you would do this step of such a workflow. So we've got our damage simulated and we know what's going to be down. If you think of the network model, here's a toy example from an academic test case. Then when you apply the damage, essentially what you're doing is just removing some components from the network. So we'll say, okay, these edges in the network are now removed. So then we're going to take this damaged network, we're going to put it into any one of these popular tools that are used by commercial industry every day. Now the challenge here is that if you put this network with damage into these tools, what's going to happen is they're going to come back and say, sorry, there's no solution to the power flow in this network. And why is that? Well, what we didn't do is we didn't by hand go in and remove some loads from the network or redispatch the generators in the network. All we did was damage the components in the network. And so this is a critical step to making sure that there's a solution to the power flow in these commercial tools. Now the challenge is doing this by hand can be very difficult. And you don't have to take it from me. There's a very famous paper from Tom Overby, who is also an author of one of the best educational textbooks on power systems. And in this paper, he says that finding a solution to the AC power flow occasions without a base point solution, like a standard operating point, is maddeningly difficult. And I can tell you from my own experience trying to do this, it is definitely very difficult to do by hand for a large network. So I've been looking at this problem for some time, and over the years, me and my PhD supervisor, Pascal van Hentenbroek, have looked at a bunch of different approaches to how to do this. And that's this set of papers you can see here are examples of different approximations you can use to try to solve these problems in practice. One interesting result from these papers is that very simple things you might try, like using a DC power flow and doing the load shedding with that, can be very difficult to convert into full AC solutions. So you really need something for this severe contingency case that's beyond standard off-the-shelf tricks. But it's important to note that all this previous work was done before the advent of convex relaxations, and they weren't widely known. So my primary goal in this work was to go beyond power flow approximations, which I had done before, and explore if convex relaxations and nonlinear programming could be used to solve this AC minimal load shedding problem on realistic data sets, like the ones that come from FERC 715 filings. So at this point, I've covered the motivation of what this work is about. Coming up, I'll begin by defining the AC optimal power flow problem. This is just review, but it'll give us a good foundation for where we're going to go with a minimal load shedding formulation. Then I'll show you how you could think about adapting the AC optimal power flow problem to an AC problem with damage integrated into it. I'll do some preliminary testing of that kind of intuitive model and show you some of its drawbacks. And then I'll take that preliminary model and we'll do some revised formulation based on the testing, and we'll make a new proposal. And finally, we'll do a very detailed experimental validation of that new proposal. So what is the AC optimal power flow problem? Some important preliminaries to know is that we will accept Matt Power's AC mathematics as kind of our ground truth. The mathematics that are in Matt Power are capture about 90% of real-world data sets, so I think it's a very reasonable mathematical model to start off with. Everything presented in this talk will be in complex numbers by default. So uppercase letters indicate complex numbers, lowercase letters indicate real numbers, and then bold values are constants, and non-bold values are decision variables that you're trying to make. So here's an example of what the network diagram looks like. And I'll just go through each one of these components and talk about what data we have for each of them. So each one of these lines is a bus. It has a complex voltage V, and then we also have bounds on the magnitude of that voltage. Usually it's within 0.9 and 1.1 or something like that. These circles indicate generators. Generators have a complex output, and they have a bounding box both on the real and reactive power of that complex output. And then we'll also assume we have a cost function, so for example, fuel cost for each generator. This little arrow indicates a load. We're assuming that loads are simple constant power loads, but it's also a complex number. For this icon indicates a bus shunt, which we just assume is an admittance to ground with the value y. Then for each line, we have three values. We have an admittance y, we have the thermal limit s, and an angle limit theta. This little line is indicating line charge on the lines, so they can have that if they're very long. And then in some cases, these branch models will also have a t variable, which represents a transformer. Combining all that data, we'll use Ohm's law on the lines. So this defines the physics of how power flows along those lines. And then we'll also use Kirchhoff's current law to balance the power at the buses. So this is a simple conservation of flow type of constraint. Now, when I do purely academic work, this is kind of where I would stop with the equations. But in this case, because we're really targeting realistic data sets, we also have to include transformers and bus shunts and line charging. So this is what those equations turn into when you add in these additional parameters for realistic data sets. So here's where the line charging value comes in, here's where the transformer parameter comes in, and this is where the bus shunt value comes in. And as we'll see later in the talk, this is actually quite important, all of these details. So taking all those equations and all that data together, we can now state what the optimal power flow problem is. So here's a mathematical program, which is modeling the AC-OPF problem. So I'll just walk through each of these. This models the voltage bounds on the variables. This models the generator bounds. This models Kirchhoff's current law. Here's Ohm's law on the lines. We have our thermal limit for flow on the edges, and then our angle limit for flow on across the edges. This is the fuel cost objective function, and that's the complete AC-OPF model. Now, the first question you should be asking yourself is, what kind of mathematical program is this? Is it convex? Is it non-convex? Is this an easy problem or a hard problem? And just by looking at this constraint, you can see that it makes a donut-like feasible region. And so that indicates immediately that it's a non-convex problem, and that should raise some concerns because that class of problems can be very difficult. And in fact, there's a very nice paper which explains that even if you have a simple tree network, it may be NP hard to determine if you have an OPF solution to that particular tree network. So this can be a very challenging problem. Now, what is the main issue with non-convexity? The main problem has to do with how interior point method algorithms work. So here I'm illustrating a general non-convex region. And imagine that you start running your interior point method at two different locations. You'll kind of follow towards the objective until you hit the boundary, and then you'll move off until you get to a local minima, which is indicated by each of these orange lines. So the pros of interior point methods on these non-convex problems is that they produce a feasible solution. So if they converge and they say, we found a solution, it's feasible for all the problem constraints in your problem. The big disadvantage is that you have no algorithmic guarantees, both for the quality of the solution, like optimality, but also for feasibility of the solution. It may converge to an infeasible point even when one exists, and you just don't know if one exists or not. Now, in contrast, if you have a convex relaxation of this interior point method, things are a lot different. No matter where you start inside of this region, you'll converge to one of the global optimal solutions. And so the big pro here is that you have a guarantee of optimality and also a guarantee of feasibility if the problem is feasible. The big con is that there's this type of formulation can cheat. It can take advantage of the convexity to go to a place where the non-convex model cannot go, and then produce some kind of better solution or feasible solution that isn't possible in the non-convex model. So the main idea here was to explore, how can we do this convex relaxation thing for the severe contingency case. So here's our OPF model. The natural question is, how can you convexify this thing? The first key observation to make is that all of the non-convexities in the problem come from these V product variables. Everything else is either linear or convex. So basically, finding a convex relaxation is a matter of how are you going to deal with the product of these two complex numbers, Vi and Vj. What we're going to use as an example and as a basis for this work is a very simple second-order cone relaxation, which is one of the oldest relaxations to be proposed. And the key idea here is that we can lift variables, this vi, vj product, into a new variable. We'll call it wij, and then introduce a valid inequality, which is that the magnitude, the absolute square of w, is less than or equal to the product of these two other w variables. So this is what the AC-OPF problem looks like when you relax it to be the second-order cone OPF problem. And what you can see is that every place we had a voltage, we've now replaced it with the w variable, and all of these constraints are either linear or convex. And in addition to replacing all the v products with w, we also add in a valid inequality here to strengthen the quality of the relaxation. All right, so that's the basic review of optimal power flow and second order cone relaxation for optimal power flow. How can we adapt that formulation to supporting component damage and ultimately solve this severe network and damage analysis problem? So here is what like an illustration of a network diagram for a power network. Now let's imagine what happens if you damage this collection of lines in the network, just to build our intuition for what we're trying to do. What you'll see is that a bunch of the loads in this network become isolated from all the generators in the network. And mathematically, what this means is we have something like Kirchhoff's current law, which looks like this, and we've eliminated all the generators, all the shunts, and all the line flow because there's no generators in this network. And we end up with an equation that looks like the demand at every node needs to be equal to 0, but we know it's not 0 because the S is a fixed parameter in our model. So the first idea is we have to allow the load to be shed or removed from the network so that when buses get isolated, we can deal with this kind of problem. So yeah, the intuition is that we need to be able to shed loads, and that there's a trivial solution to this power flow problem if you set all the loads to 0 in the system. So that's where the load variable occurs in the power flow problem. How are we going to modify this? We're going to modify it into this particular formulation where there's a lot of things the same, but a few are different. We've introduced a new variable, ZD, which can be in the range of 0 to 1. And then what we've said is we multiply the power at each bus by this ZD variable. So this implements what one would call a constant power factor load shedding. Both the active and reactive power scale down together in the same proportion, down from their nominal value down to 0. And then the last little thing is that we're going to say that we want to maximize the amount of demands that we serve in the network, or you could also think about minimizing the amount of load that's shed. They're both equivalent. So the main question, this is fairly intuitive, is this a sufficient formulation to solve this AC minimal load shedding problem? Now, I'll just take a little diversion and talk about why it's hard to answer this question. What we have here is a non-convex AC minimal load shedding problem. And so, as you know, the non-convex methods can go to different points. And more importantly, when the solver, when you put this problem into a non-convex interior point method and the solver says there's no solution, you don't know if it's your algorithm or if it's the formulation of your problem which is the problem, because both of them could be the cause for infeasibility. Now, if we think about a convex relaxation of our problem, this has the main advantage that if the solver says infeasible, it means that the formulation has to be the problem. So there's no, if a convex optimization has a feasible solution, an interior point method will find it, up to, say, floating point precision issues. So the key idea we're going to use now is we're going to use this convex relaxation to try to diagnose issues that we have in our non-convex formulation. So how do we make the current AC load shedding problem into a second order cone relaxation? Well, we're going to play the same trick we did before. we're going to introduce these W variables and then add this valid inequality. So now we have a hybrid of the AC load shedding and the second order convex relaxation that we saw before, and we use the shorthand SOC-MLS for this. So you can see here are the differences, that we still retain that load shedding part of the problem. So how are we going to test this SOC-MLS formulation? Well, the approach I took was that I took the relaxation, I took a standard IEEE test case, the RTS-96 network, which is a small but very well curated test case. What I did was I checked all of the N-1 cases where you remove one bus, one generator, one branch, and then I took 1,000 randomly generated cases where I removed 30% of the branches in the network, so a very severe contingency case. What I observed after doing this analysis is that the solver converged 99% of the time, but in about 1% of the cases, there were problems with convergence. And so what I did was I looked into those 1% of cases in excruciating detail and tried to understand exactly what was wrong with them. So this is essentially a counterexamples by brute force. We just sampled a lot, and then we looked for counterexamples where the second order couldn't converge. So here's one of those examples of an infeasible case. So basically there's a bunch of branches damaged. I go through the network, I indicate which ones are damaged, and then just using my human intuition, I guessed that this was the cause of the problem. So what this diagram indicates is that you have two isolated nodes. They have loads attached to them, but they also have, the line indicates that there's some line charging there. So by isolating the line charge, somehow we've made the problem infeasible. And when you look at the math, it's pretty obvious why that's an infeasible case. Here's another example that popped up. If I damage that particular node in the network, I've isolated one of the bus shunts. And then again, this is an example where we not only need to be able to shed the load in the network, the constant power load, but also the bus shunts effects as well. So we need to be able to shed this as well. Another interesting case was one like this, where essentially one line goes down, and then you have a whole connected component without generation, which is right here. And for some reason, this was causing difficulty for the numerical method to converge, even though mathematically, if you remove all this, it's the same. That kind of pre-processing seems to be very helpful for the numerical methods. So those are just some intuitive examples. There were more examples out there, but making a long story short, what we discovered was that this AC-MLS formulation requires at least 4 key features. You need to be able to shed the loads. You need to be able to shed the bus shunts. Interestingly, you need to be able to uncommit generators, because in real networks, generators can have lower bounds of, say, 20 megawatts or something like that. And so if you isolate them, then there's no feasible way to dispatch power from them. So you need to be able to uncommit generators. And last but not least, you need to be able to remove buses entirely from the network, because sometimes you can't meet the voltage bounds, and the easiest way to address that is just to remove the buses entirely. We also found a couple of helpful pre-processing steps just to improve convergence and reliability of the algorithms. The first one was that we should remove dangling buses. When you have arbitrary damage to the network, you can have this case where you have a line and a bus connected to it, and the bus has it's like dangling and it has no load or generation. So it really doesn't serve any purpose. So you should just pre-process those away. You should also remove connected components without load or generation before you start solving. And last but not least, it helped to solve one connected component at a time rather than solve them all together. So armed with these insights from brute force counterexamples, we can go back and we can revise our AC minimum load shedding formulation. So here's the final formulation we came up with in this work. And there's a lot more complexity, so I'll go through it. We're going to have 4 different types of decision variables added to the problem. We're going to have discrete variables, which should be 0 or 1 for whether you have a node in a network or a generator in a network, so you can just kind of remove them entirely or not. We also decided to allow both the active power demand and the shunts at each bus to be able to be scaled linearly between 0 and 1, with the idea that at the transmission level, these components are modeling kind of aggregations of lots of things. So a non-discrete model is a bit more accurate for how to model those. But these decisions are somewhat arbitrary, and if you have a more detailed model of your network, you might make slightly different decisions. These particular constraints add those discrete variables that go from 0 to 1 on the nodes and the generators in the network. So this is what allows you to remove them from the network. Then we also have the continuous variables, which enter Kirchhoff's current law here and allow you to shed the load and bus shunts from each bus in the network. Now, what we're going to, and last but not least, we have now a multi-objective. You can see that the last term in the objective maximizes power demand, but we decided that first you should try to keep as many buses in the network as possible, then keep as many generators in the network as possible, then meet as many of the shunts as possible, and last but not least, serve as much active power load as possible. So given this formulation, the kind of basic form of it is an AC minimal load shedding problem, which is a mixed integer nonlinear program because we have discrete variables and continuous variables. In this work, we study 4 variants of this problem to try to understand, what aspects of it are really key to a high quality solution. So one thing we look at is a second order cone relaxation, SOC, where we look at the voltage product non-convexity and we relax that to a convex set and see what happens. The other thing we look at is this continuous relaxation version, -C, where we say, okay, these discrete variables, which should be 0 or 1, can actually vary in the range of 0 to 1. It's also important to note that most commercial solvers do not support this kind of lexicographic multi-objective problem. And so in practice, what we do is we use some scaling parameters, different ones for each one of these components, and we add each of the objective functions together to convert the multi-objective into a single objective. If you're careful about how you select these M values, you won't change the optimal solution. And in the technical report, there is some guidance about how we set these particular parameters. So given these 4 variants of the problem, what are the key questions we want to ask? First, we want to ask, do non-convex solvers just kind of work on this problem in practice? We've observed that with the traditional optimal power flow problem, if you use a non-convex solver, it typically gives you a very good solution. So it's very reasonable to use a non-convex solver in those cases. And then if that is true, you want to know how big is the optimality gap. Are those non-convex solvers getting close to a global optimal solution, or are they very far away from what the lower bound suggests is the best possible solution? The next question we want to ask is, how much do we lose by convexifying? Is the convexification from AC to second order cone the key piece we should be careful of, or is it the relaxation of the discrete variables to continuous variables? And in particular, which problem features are important to getting a good solution to this particular problem? And then last but not least, we can revisit this question, is this AC minimal load shedding maddeningly difficult? Because we do know doing it by hand is very difficult, so maybe it'll be difficult for the solvers, or maybe it won't. So this brings us to a detailed experimental evaluation of these different methods. So here's how I designed the experiment. We take PG-lib test cases, which are official IEEE AC-OPF benchmark cases, and we take a range from 73 bus cases to 6,000 bus cases. The goal here is to capture both scaling properties of different algorithms and to get to a size of cases which are realistic. So 3,000 or 6,000 are getting into the range where you're really modeling a transmission system at its full level of detail. For each of these networks, we're going to take 1,000 randomly generated n-30 damage scenarios, and we're only focusing on damaging the branches. We selected this n-30 branch scenario case because it was the hardest case to find feasible solutions in a study we did in 2011. So it's kind of like a stress test of the method. Now, each of these formulations spans a lot of different types of problems. We have mixed integer problems, nonlinear problems, mixed integer second order cone, and these are the different solvers we use. We use Bond-Min for the mixed integer nonlinear programs. We use Pajarito for the mixed integer convex programs, and we use IP-opt for the convex piece and Gurobi for the mixed integer piece. And then for the continuous problems, second order cone or AC nonlinear, we use IP-opt compiled with the HSL linear algebra library. And using the HSL library is actually quite valuable and important to getting good performance and reliability. So here is an overview of the convergence quality and runtime of all those different methods on all these different problems. And because this is a lot of information, I'll go through and highlight some of the key points. The first thing to observe is that for small networks, like the RTS96 case, all of the methods perform pretty well. So even the non-convex models are converging 98% of the time. Maybe it's a viable strategy to just use those directly on those particular models. Now, the story becomes a lot different as the networks get significantly larger. Then feasibility of the non-convex formulations becomes a serious challenge. So you can see that the mixed integer non-convex is getting error or hitting the time limit 70% of the time in some large cases, or just hitting error 80% of the time. For the continuous version of that, there's also issues with convergence, especially on this RTE 6000 bus case. Now, in contrast, the second order cone relaxations are converging almost 100% of the time. There's maybe 0.5% of cases where the mixed integer version doesn't converge, but they're quite reliable. And then if you look at the runtime, it's actually quite fast. So the mixed integer problems, you can't really get away from some significant runtime because it's a discrete problem. But for the continuous ones, on average, you're looking at less than 30 seconds runtime, maybe even less than 20 seconds in runtime for those particular problems. So overall, this looks like the fully relaxed problem with the second order cone relaxation and relaxing the discrete variables has a lot of potential. It's very reliable, very scalable, and just really fast. So the next important question is, what do the optimality gaps look like? Because even though this formulation is very reliable and scalable, maybe its quality is really bad as well. So this table summarizes the optimality gaps, and you'll notice that the number of cases is getting smaller and smaller as we get to bigger cases. And the reason for that is to measure the optimality gap, we need a mixed integer AC feasible solution. And as the problem gets bigger, our Bond-Min becomes weaker and weaker for providing feasible solutions. So then we can't measure the gap. But we take the set that we have feasible solution for and we measure the gap. And what you can see is that these gaps are incredibly small. So this is not, this is in percentage. So you're looking at like 1/100th of a percent or less than 1/100th of a percent in the gap. So that looks very promising for the quality of the relaxation, but we won't know for sure until we can get a feasible solution for, say, all the problems. So yeah, those are the gaps. You can see that these gaps are very tight, and they're not so bad compared to the other ones. So it seems like you're not losing too much by using this very relaxed problem. Now, just to show you that even without an AC feasible solution, this can produce some interesting results. What I'm showing here is a proof of concept study for how you could do load shedding using this formulation. So I've taken each of those networks, all 1,000 cases, and what you're seeing is the distribution of load shedding across those cases. So the interesting thing here is that both the mean and the variance of these large-scale branch damage cases is quite different in all these different networks. So you can see like the width of the distribution is very different in different networks. Also, the mean value is very different. So it seems like there's quite a lot of variety in how a random damage to the branches would affect each of these networks. It's worth noting that this kind of threat is similar to something like a hurricane or maybe an earthquake, where every component in the whole area has an equal probability of failure, and then they just all fail based on random chance. So there's a great variety in these distributions, and I think it's an interesting open question, what features of the network lead to this variability? And it's worth noting, or it's very important to note actually, that these distributions are on the lower bound of load shedding. We computed these with the relaxation, SOC-MLS-C. And so they could actually shift to the right depending on how close we are to AC feasibility. We expect them to shed more than this. But at the very least, we have to shed this much, and there's quite a bit of variability there. So that gives you an overview of what we're doing. I'll just wrap up with a couple of conclusions. First off, one thing I learned from this work is that this very, maybe I would say weak or very relaxed formulation, SOC-MLS-C, is surprisingly good. It's kind of shocking to me how strong a relaxation it is, given that we relax so many things. This study also seems to indicate that if you combine convex relaxation with random test generation, it can be a really nice methodology for finding good formulations. So you can use the relaxation to prove inexistence of the AC problem for those hard cases, and then know your formulation is really problematic. And in this particular case, it seemed to work really well for finding all the special cases we needed to address with this AC-MLS formulation. So in future work, we're going to be using this convex relaxation to then build AC feasible solutions for the real problem we want to solve with both those discrete variables and the non-convex physics. And last but not least, I have to give special thanks to my co-authors, Russell, Byron, Karthik, and Scott. They all played an important role in making this work a reality. So thank you much for listening to this. I hope you found this work interesting. On arXiv, there's a technical report with all the technical details, and please feel free to contact me if you have any other questions. Thanks a lot.